Hello and thank you for watching. In this video we're going to go through monotonicity and subsequences. So firstly, let us define what we mean by monotone. So monotone means that something is either decreasing or increasing, which may seem like it's the case for everything. We have every sequence, every function, but it means that once we start decreasing or once we start increasing, we don't go the other way. So for example, let's say some sequence xn equals 1 over n. Now clearly we have 1 over 1, and then we have 1 over 2, 1 over 3, and as we increase our denominator, every term gets smaller. So we keep going and going, and this means it is monotonically decreasing. In fact, we see that it's never equal to the previous term. That is, it is strictly monotonically decreasing, which means that for every xn we have, that the next term, wrong sign, the next term is smaller than the previous term. It is only monotonically decreasing if we have an inequality here. So for example, if we had something that could have something like this, like where the terms over here are equal. It looks a bit like x cubed, but yes. Carrying on. Let us define what subsequence is now. So subsequence. Okay, so firstly it's a sequence. So suppose we have xn. It's then a subsequence is a sequence that takes n1 that is less than n2, that is less than n3, and so on, with xn1, xn2, and so on. So for example, say we have xn equals 2 to the n, for example. Now if we have x2n, this is equal to 4n. This is clearly a subsequence because this sequence goes 2, 4, 8, 16, 32, 64, and so on. Whereas this one goes 4, 16, 64, and so on. We see that every term from this sequence is also in the sequence above, and we take every increasing index term. Now, an example of something that's not a subsequence despite being a subset of the sequence from before is something like taking x 2 plus cos pi n. That gives us x1 and then x3, then x1, and so on. So in this case, it would be 2, 8, 2, 8, and even though every term from this isn't there, the index is not increasing, therefore it's not a subsequence. Okay, now we're quickly going to prove one theorem. Prove, or well, every subsequence of a convergent sequence has, or with limit x has limit x as well. And it's kind of what you'd expect, since, well, suppose we have a convergent sequence such as 1 over n. If we have some subsequence like 1 over 2n, we expect it to go to the same thing as we go really, really big, as long as there's a value it tends to, for the reason that we'll carry on sharing the values. So it won't, this for example, won't suddenly spike up to a different value. It will be around the same point, even though they're not taking the exact same values for every index. Okay, so to prove this, suppose we have xn converging, we should write, suppose xn converges to x, then for n being greater than n, or for all epsilon greater than 0, there exists an n such that n being greater than n, we have that xn minus x is less than epsilon. Okay, so now what we're trying to show is that, in fact, we have this as well. Okay, so first thing to note is that since for a subsequence, since we need to have n1 being less than n2 being less than n3, and so on for our indexes, we have that every index of the subsequence is greater or equal to the index of the sequence itself, which is greater than n from what we had here. That is, nj is greater than n itself, because we can just ignore this term. Okay, and, well, we have that xnj is every term in xnj is also a term in xn, since it is a subsequence. So because of that, we have for nj being greater than n, we also have xnj minus x also being less than epsilon. So that is xnj goes to x as well. Therefore, xn and xnj converge to the same limit if xn converges. Okay, and that's it for this video. Thanks for watching. Hopefully this helps you understand monotone sequences a little bit, along with subsequences. And yes, thanks for watching. Bye bye.